Welcome everyone to NIDays. Thank you very much for coming. For this, I would like to invite Mr. Shekhar Sharad from National Instruments Corporate, the Senior Group Manager for the Academic Segment. Shekhar, the floor is yours.
Marhaba, good morning. It's always a pleasure for us to be here with all of y'all. I know I have a lot of friends out here, and I hope to make a lot of new ones today. So thanks again for making it here today with us. I'd like to spend some time talking about the trends that we're seeing in industry and how they relate to us in academic. As His Excellency this morning stated, it is very important for us to find ways to understand what industry is doing and prepare our students for them. And by the way, this is the most exciting time for us to be in universities. There is so much different stuff going on. You know, you hear about things like MOOCs, flipped classrooms, SPICE simulation, FPGAs, multi-core, maker movement, and the two words that make the most resonating sense from industry, systems and design. So, the question then is, how are we going to prepare our future students of 2030? To answer this question, we have to understand where industry is going. And I want to show you some examples. The main focus for industry now is to build systems. And there are different kinds of systems that you see in your everyday life. A typical car includes more than 200 microprocessors today, all of them interconnected. You have the Tesla up here, which actually has a live 3G network all the time that communicates with the satellite networks and shares data. The smartphone in your pocket is a true cyber-physical system, and I'll talk about what that means in a second. Even the simple elevator that you take, or the insulin pump that patients use to give insulin, are all examples of systems. That's where the industry is going. And we have to find ways to make our students of today these system designers, so that when they graduate from the university, they're able to go and build these systems. So then the question becomes, how are we going to make sure that our students who are going to graduate and use hardware and software to build these systems, or use the systems themselves, can be ready for this challenge? That's the big question. So, in preparing for the system designers, you have to understand the components of a system. And there are three big components that academicians have categorized systems into. They are computation, quad-core processors, multi-core processors, dual-core, all of that stuff in there, low-power ARM, everything is in that box. There's communications, which are the different types of communication architectures, 5G, FSK, OFDM, all of these things are in that box. And the last one is control. PID, state space, LPure, all of that stuff. But it's not these individual components by themselves that matter. It is the communication of information between these three elements that make up the complex systems of today. So in the past, we could get away by training students in just one of these blocks. But that's not the case anymore. We have to find ways to teach them all three of it. And by the way, the industry has come up with a term for these systems. They call them cyber-physical systems. So whenever you hear the term cyber-physical systems, this is what they're talking about. It's the interplay of communication, control, and computation to derive information that can be used to make life better. So, how do we teach students cyber-physical systems? Well, if you think about teaching in general, you have to start with the basics. And then use the basics then to teach intermediate concepts and ultimately help them build a full system. Now you're probably sitting there thinking, well, I have 4 years to do this. How am I going to solve this problem in 4 years? Well, it's actually not very different from what you do. You teach your basics in the very first year. So you have things like circuit design, introduction to PID, signal processing, signals and systems. All of that stuff is in your basic lower level layer. But then, when a student goes to the third year, they start actually stitching these different concepts together. So you can actually now teach them advanced control or the latest RF and MIMO algorithms by taking the basic concepts that they've learned in the first couple of years. And then the big one comes in. Then in the final year, probably in the final semester, the student gets an opportunity to put their own system together. And by the way, that's a really hard problem, so we'll talk about that in a second. Now, LabVIEW will work very hard to be able to help you teach the basic and intermediate concepts seamlessly. So here you can see how they've combined graphical and textual code together. And they're stitched together in such a way that you don't have to worry about, well, will the text code work properly? Will my M-file scripts coexist properly? Will my control algorithm function the way they will? LabVIEW does all that work for you. And we're working really hard to continue giving you features that help you teach these concepts better. And we'll talk about that more when we come here next year. We've got some really exciting things in the works. Now, if you look at the bottom and the middle layer, for the past several years, about 10 to 15 years, we've been working very closely with academia to deliver solutions that help you teach these concepts. So we work very hard to deliver platforms to help you teach circuits, communications, control, embedded systems, RF, even software-defined radio in a very affordable manner. And I'm not going to go through all of these details. The big thing is we worked very hard to make LabVIEW at the center of this picture easy enough and industry relevant enough so that when your students use it and graduate, they can get jobs in these different fields. But the biggest challenge is this top block. Imagine your student goes through 3 years of university, and in the final year, they're sitting there thinking about their final project. This is the one project they're going to remember for the rest of their life, because it's the one project they get to choose and they get to build. But it's not a trivial problem, right? And to make it harder, sometimes they only have 1 semester, because you want to teach them a lot of theory. Now, there are several different ways that people have tried to solve this problem. They're really low cost, really limited computing power elements that don't really help them build a full system, like this one here, which our friends from Conjure will talk about soon. On the other hand, there are very powerful platforms that are very expensive and very hard for people to use. And you cannot get anything useful done in 1 semester. So when National Instruments thought about this problem, we took it upon us as a challenge. And we've taken on other challenges before. For example, in 1986, we went to our founders and said, there has to be a better way for engineers and scientists to design systems and program. And in 1986, as you're aware, we launched LabVIEW. This is a very young Jeff Karosky, who's the father of LabVIEW, showing the very first version of it. Overnight, engineers and scientists around the world had a better way to program their systems. We didn't stop there. Professors like you came to us and said, we don't want to invest in expensive benchtop instruments. Is there a way by which students can get a single platform that can help them learn instrumentation? So in 2004, we launched the ELOS. And overnight, universities around the world had access to a very cost-effective platform that put together 12 instruments in 1 box. In 2004, this was a very big deal. Nobody else was doing it. And we were the pioneers in this field. Well, more recently, you all came to us and said, well, this is great, but it's still in the lab. Is there a way by which we can take the power of this platform and put that in a student's backpack? So in 2010, we announced the NIDays. Another revolution where we took the power of instrumentation and data acquisition and put that in every single student's hands. Now, we also tackled other hard problems, like teaching MIMO and software-defined radio for a relatively inexpensive price, so that every student doesn't have to worry about paying a $50,000, $100,000 RF equipment, but do it more affordable. So in 2011, we came up with the NI Universal Software Radio Peripheral and changed this space as well. By the way, we've got something very exciting in this space that Nancy will talk about today. So look forward to that. So, we're back to this question. How do we redefine student design? We went back to our R&D and we gave them a checklist. We said, if we're going to change this space, we need the following requirements. First, students have to get the full lab. It cannot be one toolkit, it cannot be one module, it cannot be that MathSmith doesn't work. Everything has to work. And then we said, professors shouldn't have to choose between an FPGA or a DSP or a microprocessor. They should have access to all these different elements on this one platform. And then we said, students don't have to worry about picking the different I/O ports. If they want analog input, they get it. If they want analog output, if they want PWM, if they want UARTs, if they want SPI on there, they should be able to have access to it. Right? And then all of this is useless if you cannot connect the sensors and actuators around you. So this has to work seamlessly with the sensors and the ecosystem that's out there. And all of this is useless if it takes 10 hours for the student to use this in a program. So we gave them a challenge. We gave R&D a challenge. We told R&D that this device should work within 5 minutes of opening it for us. That was the challenge we gave. And we said, if it does all this, but it's assigned to this rule, then it's useless. So it has to fit in a student's backpack. Every single student must be able to carry this with them and their project with them. And of course, inside the backpack today, students also have one of these, right? An Android or an Apple tablet. So we said, this device better work with that as well. And because of that, it has to have Wi-Fi. So we gave R&D this checklist. We said, we want a platform that is rich, known I/O, is built on industry standard technology, that is Wi-Fi enabled, tablet ready, fits in your backpack, and you can get up and running in a relatively short time. And we're really proud today to announce to you, ladies and gentlemen, a revolution in student design, which we call NI. And we'll show you this device now in action. But before we go into a demo, let me walk you through this product real quickly. First, it's based on the most advanced silicon that's available in the industry today. My background is embedded systems. And when I did my master's, we learned about this term called system on a chip. Well, it was theoretical at that point. It didn't exist. This is the first manifestation of a system on a chip. It has an FPGA on it, it has a DSP on it, it has an ARM, actually a dual core ARM on it, and all of them work together. And you can program any piece of it. It is the most advanced chip available on Earth. And it is inside the market. Now, let's talk about the device itself. We took great pains to make it student ready. On the back of it is a built-in accelerometer. There's also mounting holes for students to build robots and projects. And you would think that's a trivial task, but there are a lot of PCBs out there that people sell that is very hard for you to build a robot on because of ESD and stacking and everything. That problem goes away. We also focus a lot on the getting started experience, and we have lots of tutorials that you can look at. Now, if you look at the top of the device, you can connect this to your computer through USB and download the code via USB. And it's an FPGA platform for this. So if you all know Compact Rio, you know that it cannot program with USB. This device you can. There's another USB port out there, and this is interesting because it runs Linux on it. So you can connect webcams, you can connect USB flash drives, you can connect any USB peripheral that you want. And by the way, the power, you can run this with AA batteries for 3 hours for doing experiments, which is pretty powerful. Now, let's talk about the I/O. On this side, take every number you see here and multiply that by 2 because you got 2 connectors. So you have 8 analog inputs, 4 analog outputs, 12 digital input outputs, 2 quadrature encoders, 2 URs, 2 SPI, 2 I2C, 6 PWMs. Right? That's a mouthful. Now, that's not all. On the other side, this must be familiar to you because it's the same connector that's on the MIDays. So you get an additional 2 analog inputs, an additional 2 analog outputs, 8 additional digital input outputs, and audio jacks that you can use for it. So this is the whole package. And by the way, it runs the whole LabVIEW. And when I say the whole LabVIEW, I mean every single toolkit and module we have. LabVIEW Real-Time, LabVIEW FPGA, LabVIEW Robotics, LabVIEW Vision, MathScript Real-Time, Control Design and Simulation, you name it, it runs on this device. But hey, I've done enough talking, right? I'm sure you guys want to see this device in action. So to do that, I'm going to invite on stage Margaret Beirut, who's the product manager for this product. Margaret?
It's such an honor to be in Lebanon today to get to talk about this great new student design device, but we've talked about it a lot. Let's see it in action.
All right, so Margaret, we've made some pretty outlandish claims to the audience. Right? We've said that you can actually use this device and get started and running within 5 minutes. So are you ready for the challenge?
I'm ready, let's do it.
All right, let's go for it. But wait, hold on. This is pretty serious. Let's actually time her. Do you all have a smartphone on you? Hopefully everyone does, right? He's looking at this watch. That works too. So I have my smartphone here. I encourage you to join me on this one. Margaret, whenever you're ready, we'll get started. Do you want to switch the input?
Oh, yes.
All right. Wait, don't start the time yet.
All right.
Whenever you're ready, Margaret.
Okay, so I'm ready. Let's go. I have a MyRio here with just power connected at this point and a USB cable. I'm going to plug that right into my computer, and we should be able to see the same experience that a student is going to see the first time that they plug in a MyRio. So what I'm going to do here is click Launch the Getting Started wizard. That seems like a good place to get started. And the Getting Started wizard is going to allow us to configure our device and set it up to use. So it sees my device here. I click Next. And this is now checking to ensure that the proper software is installed on this device. And if it's not, it will take care of that for me right here. I can rename it if I need to. And now when I click Next again, Shaker, how much time have we elapsed so far?
48 seconds.
Okay, so in 48 seconds, we've plugged in our device and already gotten some data.
So this is acquiring from the device. Those are the 3 accelerometer axes that you're seeing there?
Exactly. So 3-axis accelerometer, user-defined button, and we're also able to test out the 4 programmable LEDs that we have on MyRio.
Right, but Margaret, I thought we were going to program this in LabVIEW.
Okay, so let's keep going. So when we click Next again, now we have the ability to get started with the tutorial if we're new to LabVIEW and new to MyRio. So I'll click on that, and what we'll see is that it opens up LabVIEW, and it also gives us this nice tutorial here that we're able to follow, and it's going to teach us how to programmatically recreate what we just saw on that test panel. So we'll pretend that we read that, and we'll come into LabVIEW and create a project. There we go, and we have some MyRio specific projects here that we can choose from, so I'll just choose a MyRio project. I click Next. Here I'm able to name my project, save it, choose how the MyRio is connected.
Wait, I see Wi-Fi there? So
That's right. So right now I'm having it connected over USB, but I could program it over Wi-Fi if I wanted to.
I think we're going to show you that too, so hold on.
So I'll click Finish, and this will build up for me a LabVIEW project with the MyRio already ready to go in it. So here's a VI that I have ready to run. Take a look at the block diagram really quickly. It looks like we're going to read from the accelerometer, so I'll just run this. And now what it's doing is it's actually deploying this code out to the processor here on MyRio. So this code actually isn't running on my laptop, it's running here. And it looks like we're running some code.
So we're deployed, and I have 2 minutes, 40 seconds. Does anybody else have a time check for me? Awesome, 3 minutes? 3 minutes, that's pretty impressive. Good job, Margaret.
All right.
Now, I know you went under the gun, so you did all of that really fast. But could we give the audience a little bit more deep dive on the software and what enhancements were made?
Absolutely. So if we come take a look at the block diagram, if we right-click, we actually have a MyRio palette here in LabVIEW for us to use. So you'll see that we have these blue blocks that we call express VIs. These are configuration-based VIs, so we don't have to do a lot of programming to get access to the I/O. And we have one for every I/O type that we've predefined on the FPGA. But of course, we don't want students to think that programming is just magic. We want them to understand, how do these blue blocks work? How does the data actually get into the MyRio? So what we've done is if you double click on any one of these express VIs, each one of them will have a view code button. When you click on that button, this will actively script the lower level code that's running underneath that express VI. So we're hoping this gives students a window into some more advanced programming. And once they feel comfortable, they can actually copy this to their clipboard, paste it on their block diagram, and begin programming from this point.
So let me understand this properly, Margaret. You're telling me that I can teach a student introductory concepts with those blue blocks, but then if they're advanced concepts, you can have them go all the way down to the pin and program them. So it's kind of like choose your own adventure.
Exactly. So it's a gradual approach to some advanced concepts. And students can access these more advanced VIs to program with right here on the MyRio palette. And as you said, Shaker, they can double click into any one of these and get down to the very pin on the FPGA.
So this is cool. But I also told the audience that they can connect to pretty much any sensor or actuator around them, right?
That's right.
So can we show them something that actually connects to sensors?
Sure. So what I brought with me today is a little circuit on a breadboard here, made to plug into MyRio. And I have on it a light sensor and a buzzer. So I was thinking maybe we could play with those two components and see what we can do.
What can you do with a light sensor and a buzzer?
All right, hold on. So I'm just going to plug this right into the MyRio here, and I'm ready to program. So I'll just right-click on the MyRio and create a new VI, and we'll program from scratch and see what we can get done pretty quickly.
Margaret, you must understand, I've given the keynote here 3 times. We've never programmed live in front of them. So congratulations.
Today is the day. Okay, so the light sensor is connected to an analog input. So I'll use our express VIs and just put down an analog input here. And I can name this whatever I want. So I'll name it light so we remember what it is. And then to drive the buzzer, I'll need a PWM. So I'll put this block down. And this block's a little more interesting because here I have the ability to set things like frequency and duty cycle to be either programmatically manipulated and changed or to be constants. So I'll set duty cycle to constant to be half up, half down, and click OK. And now, because I've done this before, I know that I'm going to need to amplify the signal coming from the light sensor. So I'm just going to put down a multiply and multiply this by a constant of, say, 500. I'll wire that to be the frequency of the PWM.
So you're going to change the frequency with lights. Are we building a musical instrument?
Yeah, so we can actually build a little musical instrument out of this basic circuit.
So I did not know this, but it's called a theremin. That's what the instrument is called.
That's
so
right.
we're going to build a theremin.
So I'm going to put all of this code in a loop, so it'll run continuously. But then another thing that's cool is because this is actually going to run on the MyRio, I don't need a user interface. We'll be able to hear the sound. So what I was thinking is I could use the button that's on the MyRio to stop this code. So what I'll do is go to our onboard palette here and grab a button, Express VI. So this will give me access to the user-defined button on MyRio. And I'll make that the stop condition of the loop. And my final step is just to close out my reference to the hardware here.
Because it's an embedded system.
Right. And then I use my favorite LabVIEW button and clean this all up so it looks like I programmed it really nicely.
Very neat.
And I'll click run. And again, this is now going to deploy out to the MyRio after I save it.
So it's compiling and downloading on there.
Correct. And so hopefully you can hear, maybe you can hear here. It's a lovely sound.
Can anybody hear it there? Back? All right.
And as I'm moving my finger over the light sensor, the frequency, the PWM is changing. But I don't need this computer anymore. So what
I was going to ask, you still have the USB cable?
It's just and here I have a battery that's powering the MyRio, so if you can still hear, it's still running. But when we've had enough of that sound, we can hit the button, and now it's done.
Okay, so that's cool, but hold on though. We just told the audience that this device needs to have Wi-Fi on it, and you can walk around and do stuff with it. So can we now connect this via Wi-Fi and kind of look at it?
Absolutely. So I have a project here that I've already built that will let us use a tablet. I have an iPad up here with my Rio, and we'll access all of our data over Wi-Fi. So let me just open up this project. And what you'll notice is if anybody has their phone out, you'll see a network that's being broadcast right now called My Rio. Hopefully you can't connect to it because I put a password on it. But what this is a network that's actually being created by this device. So My Rio can actually act as an access point and create its own network that we can connect up to 6 devices to.
Okay, let me understand the point correctly. So you're saying that when you use My Rio, you don't need a Wi-Fi network in the room.
That's right, we can create our own.
So a student could create a robot with this, put it in the field, right, and have them monitor that with their computer?
That's right.
Wow.
So here, let me drag this over. We have some code. This is just reading from our accelerometer again, but this time we're publishing the data out to shared variables that are going to be deployed out on this My Rio network, and I'll be able to access them from things like my phone, Android, iOS, or my tablet.
Wow.
So we'll just give this a run, and right now, as you can see, the My Rio is not connected to the computer at all. So I'm deploying code to this My Rio without any connection to my computer, except for Wi-Fi, of course. And here's data on my computer, but I'll also show you that I've created a data dashboard front panel here on my iPad. So Data Dashboard is a free app available in iOS and in Android. So the same data that I'm seeing here on my computer, I'm also seeing here on my tablet. But one of my favorite features is it's not just for monitoring data, I can also send data to the My Rio. So here I have a stop button, and when I press it, our code is stopped.
Wow, and you did it all through the iPad.
That's right.
And by the way, the app that you talked about, that's free?
It's
that's available
free.
on the App Store or the or the Google Play Store?
Correct.
Okay, so all of us can use this today on our Google Play or Android store. Margaret, this was really exciting. You walked us through a bunch of different things. You showed the getting started experience, you showed how we connect the sensors, you showed the Wi-Fi deployment and Wi-Fi capability. Margaret will be here today and tomorrow, so she's got a lot more stuff that she can show you. Feel free to talk to her after this so she can give you more details about this product. Margaret, thanks a lot. Can you switch the input? Just make sure we get this right here. Yep, sure. All right, I'm going to conclude real quick. So you saw that Margaret showed you how the device actually works. We've gotten feedback from you all that we need additional kits around it. So we put together some kits. We can talk to you more about it after the keynote, but it spans everything from getting started to embedded mechatronics. We also have free courseware, which you can use and customize it. We also have a cyber physical systems courseware that we talked about in the beginning. It's available from University of California, Berkeley. Our friends at AUB in Lebanon are also building courseware for this, which is very exciting for us to work with, so you'll see a lot of that come out soon. And then finally, we know we love LabVIEW, we're the NI company, we get it. But we also got a request from you that people love C and C++. So not only is My Rio programmable with LabVIEW, it's also programmable with C. So you can do it for free today with the Eclipse toolchain, so you don't have to use LabVIEW if you don't want to. So we've given you the capability as well. So we are very excited about this product because we believe that it's the ultimate student design platform and it lets you do engineering. But it's not the end of the story. I want to invite over Keith Blanchet from Quanser, who's going to show you how they're leveraging NI technologies and their state-of-the-art control plans to help students learn cyber-physical systems. So please welcome Keith Blanchet.
Thank you, Shaker. Morning. Thank you. Thank you, Shaker, again. It's great to be here again. I've been here a couple of times so far. It's a great city. What is Quanser? So some of you may not know Quanser, although we are a global company. Quanser is a Canadian-based organization, and we're focused solely on making your lives easier as educators and as innovators. We've been around. There we We've been around for 25 years, and we're well known for our expertise in mechatronics and controls. In industry, government labs, and even academic labs, research labs, we've done a lot of work in the field of robotics, haptics, unmanned vehicles, and have helped a lot of you innovate in those fields. But really, the driving force behind Quanser is education and training. As you guys know, and as Shaker mentioned earlier, mechatronic systems are all around us. The trends are increasing in terms of complexity and fighting complex mechatronic systems in our lives, which means we have a need to train better and more effective engineers in the future. This handsome gentleman here is the founder of Quanser, Mr. Jacob Akir, who happens to have been raised in Lebanon and founded the organization 25 years ago. And back then, 25 years ago, this was a statement he made, which at the time was quite visionary, because nowadays all of us would agree with this, that students learn best in a hands-on environment, and his goal was to bridge the gap between theory and practice. But really, 2,000 years ago, or even earlier than that, Confucius said, I hear, I forget, I see, I remember, but if I do, I understand. So it's really a universal truth. It's something that we all should be aware of, and it's not new. We now need to apply this in the education systems around the world. And that's what Quanser and I are trying to help you do. More recently, this is just a statement from one professor in particular, but many people will agree with this. Dr. Eberskin from the University of Washington stated a very, very interesting statement, which we enjoy, actually. It's, if you want to help a person become a doctor, and doctors are very important and we love them, but if you want to save the world, become an engineer. And there's a couple of interesting things in there. If you want to save the world, we're aware of the global challenges that we're faced around the world right now. There are many. And the young children and the students in your institutions also are aware of these challenges, and they want to do something about it. That's why they went into engineering in the first place. They're passionate about it, and we need to keep that passion. We need to grow that passion, and we need to give them the ability to execute on that passion, and that's what we're trying to do here. And when I say become an engineer, not just get your degree, become an effective, innovative, creative engineer that will push boundaries and really innovate. So, you've seen this pyramid a few times. I'm just going to make a pyramid, the base has to be very strong. Otherwise, the pyramid is not going to sustain any complexity at the top. That base part there is extremely important. What does that mean? That means we can't neglect the process here. We can't just say, oh, I just read the book, or just come to my course anymore. Students nowadays, they need to be motivated, they need to be challenged, they need to be doing things, right? If you remember what Confucius said. So it's very important that NI and Quanser have been working very, very closely and spending a lot of time making sure that the solutions that are offered at the base of this pyramid are solid and make your lives easy to do engineering at that level. I'm not going to elaborate too much on the stitching of the concepts because Shaker already touched on it very well, but I think you get the point that as we move up, we're understanding more and more the interrelation between the concepts, how they influence each other, and that is fundamental for them to become innovators down the road. But it's not just about the mechatronics, it's not just about the hands-on, but it's understanding also how are systems designed in industry. You're getting them ready for industry. We've done many panels over the years with industry, and we've discovered that industry feels that sometimes they get, the students have touched on the theory, but they don't really know how things are done in industry. I'll just give one small example. In universities, often the students will work in silos in their own departments. So mechanical engineers will work with mechanical engineers on a project, electrical engineers will work with electrical engineers, and so on. In industry, that never happens. In industry, mechanical engineers work with the electrical engineers, with computer engineers, with business people, with marketing, with sales. Sadly, they have to do that. So it's very important to expose them to that reality, if possible, soon. At least at one point in their degree. But understanding also the design cycle, and the design process used in industry, such as rapid controls prototyping, hardware loop testing. These are concepts that they should know by the time they graduate, at least a UG program. And ideally, they're actually executing on these concepts right from the beginning, from the base of that pyramid that we showed earlier. And Quanser National Instruments have put together a range of solutions that are very powerful that allow you to do that under the conditions that we know you have to live through, which are budget constraints, size constraints, lab constraints, resource constraints. We know these things, and our solutions are geared towards solving those solutions, those problems as well. So with RCB Toolkit, which is a product from Quanser, we now take the power of LabVIEW and allow you to easily, much more easily, execute on the V cycle that you see here, which is a very well-known concept in automotive and aerospace industries for decades. It's been around for a long time. So your students really shouldn't know about this. But I'm going to move back to the basic, the fundamentals. So we developed, very recently released on April 1st of this year with National Instruments, this product here on the left, which you see, which is called the Quanser Cube. It's a good example of an experiment that is meant to help you build the foundations they need for that pyramid of knowledge. And what we're talking about here is something very compact, robust, something that really can get the students excited early on and also meets the constraints budget-wise that we may encounter. Also fully leveraging MyRio and LabVIEW, of course. But it's not just about the hardware. It's not just about the hardware, but it's about integrating the hardware with the courseware. Your needs currently are to teach specific subject. You have a curriculum. The person next to you from another institution doesn't have the same curriculum you have, or sometimes the same topic or the same course. So the name of the course may be the same, but what you're going to be covering may be different. So what we did at Quanser and with NI is we modularized the lab materials that come with the experiment so you can tailor the lab materials to your very specific curriculum needs, which is extremely important to make your lives easy. Again, the purpose of Quanser and NI in academic fields is to make your lives easy, and that's another step we've taken. We've done so in formats that allow you to edit them, modify them, transform them in any way you like. So, and Mitch is going to actually touch on this a little bit later on. So what I'm going to do is I think, well, one last step, one last thing I should mention. Very often, there's a gap between the lecture and the lab. And this we've heard again from students all over the world. You go to a lecture, you hear a lot of theory, then you go to the lab, and I'm doing engineering, but it had nothing to do with the lecture I just did yesterday. And that's often a problem because they get confused. They don't see the connection between the lecture, the theory, and the hands-on. Well, what we've done is we've taken the most popular textbooks out there. You may be using a textbook from Norman Nice or Bob Bishop or many other different authors around the world, a series of textbooks that are out there. We've taken the chapters, the sections, identified them, and mapped them to the lab materials that come with our experiments. So the student can, if they're using the textbook, they're able to make that connection to the lab and understand the bridge between the two. It's very important for the learning process. But that's enough for me for now. What I'll do is I'm going to pass over to Mitch, who will actually go through a quick demonstration of the Quanser Cube with NI MyRio. So maybe just to quickly recap on the first part if you didn't understand. The first slides that you were seeing there were basically the navigator that guide you through the different experiments for the cube, allowing you to go through the modular curriculum I mentioned earlier, pick and choose the experiments that you would like to execute on the cube. And now Mitch is actually going through the development of the VI for the cube itself as your student would do by being guided through the lab materials that we supply with these systems. So here you go.
Yeah, so I'm just going to show a simple example of applying a voltage to the cube servo motor and reading the position. So in order to do that, I'm going to use, so I have a seeded sim loop, as you can see, this VI. Go down to RCP toolkit, and I'm going to drop in the Hill initialize VI. If I double click on this, it allows you to configure and select your data acquisition device. So I'm going to browse down to Quanser devices and use the Cube Servo MyRio. Click on OK. So now that I have the DAC selected, go back to my Hill palette. I'll drop in the Hill Read VI. So this Hill Read VI enables you, just going to connect these two together. Hill Read enables you to read any I/O from your DAC, all from one convenient VI. Now I'm going to be using the encoder sensor on the cube. So I select encoder, click on OK. And then to view this result, I can go to the simulation palette and drop in a sim-time waveform. Connect these two together. So that's my reading of the motor position. In order to apply a voltage, I'll go and drop in the Hill Right. So these three VIs are the main RCP toolkit VIs to access all your I/O. Connect that, and then, for instance, you can apply any kind of signal you want. So I'm just going to apply a sine wave. So I'll go back to the signal generator palette here and drop in a sine wave. Connect that. And that's about it. So I'm going to go here, save my VI. And then I'll run it. And then you should see the pendulum go back and forth once it's deployed. So this is a simple example of just doing open loop voltage, right? So you can see I'm getting the encoder measurement here, and the servo is moving back and forth. So this gives you a simple example of open loop voltage. And from the block diagram, you can see how I can progress this VI into, for example, closing the loop. And using a PID controller, for instance, to regulate the position or speed of your DC motor. So that's one example. You could also do something more advanced. So I got here a VI that is supplied with the cube. And this is the very classic inverted pendulum experiment. So the swing up and balance controller.
Mitch, I'm just going to that was actually basic servo control. Obviously something that you would touch on in an introductory course for controls. Obviously swing up here we're talking about more advanced, based on the same platform. So the student can actually build on controlling the servo position and speed to move to the next step to more complex concepts. Again, going back to that pyramid of learning, of knowledge, you build on something you know, and it's a much easier process to actually absorb and simulate concepts.
So the swing up algorithm is actually a nonlinear energy-based algorithm here. And now you can see it swing up. And then when it goes up in the upright position, it switches to a linear balance controller. So this is an example of a task-based, more applications-based type of controller.
So if I understand correctly, Mitch, in there you had some linear control, swing up. No, non-linear control, energy-based swing up, and then the balancing was PID control. Right?
Yes.
Yes. So there you go. So you're combining some of the more fundamental PID control with nonlinear, more advanced concepts as well. And if you didn't see it because it's you're at the back, it's obviously understandable. We're going to have this outside a little bit later on, so you can come by and obviously have a look and ask any questions you may have.
Thanks. I'll pass it back to you.
And thank you very much, Mitch. And thank you, Nancy. So that's just one product. Quanser has dozens and dozens of products, up to 100 products actually, experiments that cover a wide range of mechatronics, cyber physical experiments of all kinds. And MyRio is a fantastic platform, as Shaker described earlier. It's got the processing power for beginning to advanced concepts. It has the form factor that you need for student projects or embedded applications. It really has a full spectrum. It has a price point that's ideal for the academic environment as well. And as a result of that, because of that, Quanser has decided to develop an interface, a plug-and-play interface platform to allow you as educators to use the MyRio as a platform to interface to most of Quanser's experiments in the market currently. So even if you have experiments in Quanser now, you'll be able to use the MyRio to interface to it, which is fantastic news, I think, for everyone. Which means, if you're interested in building a fundamentals lab to build the base of that pyramid, that is possible. You want to touch on mathematics, modeling, sensors, programming, you name it, it's all possible already. And you through a fundamentals lab, or you can start with that and build up to what we call an applications lab, where you're addressing biomedical engineering experiments, autonomous vehicles, renewable energy experiments, a whole wide range of industrially relevant and very interesting applications for either your research, for graduate teaching, or even undergraduate teaching. And why is this important? It keeps your students motivated. And going back to this, those are the customers, those are the people we're trying to help. We keep them motivated because it's industrially relevant, not only because of the applications, but also because of the design process that they're learning, that they will be using in industry. It's hands-on, but not only hands-on, but rigorous hands-on, making that bridge between theory and practice, between the lecture and the lab. And putting all this together, they basically get a true engineering big picture, what it means to be an engineer. So now, what we're going to do is have a look at one of that top of that pyramid, an application that basically brings a lot of these concepts together, that uses a lot of the power of MyRio, and basically puts it all together. Now, sadly, the customs people here in Lebanon decided that we wanted to play with our cue ball and kept the batteries. So I won't be able to be flying this around the room today, but we have here, you don't see it at the back, there's the Quanser cue ball, which is a quad rotor, and right on there, if you come by a little bit later on, you'll see right there we have the MyRio right in the middle. So I actually have a lot of the configurations here. Now, the quad rotor, the cue ball is basically a standard quad rotor that has a cage around it. Cage being important in the sense that it protects your investment, right? And it's obviously something that you want to do. What's important here is that the tools that come with the cue ball really make your life simple and easy. It's taken 4 years to develop all the suite of tools that accompany this system now to allow you to do things like collaborative control, adaptive control, fault tolerance systems, and name it. There are many, many different types of innovations that are taking place nowadays for unmanned vehicles. Some of the interfaces you see here basically describe are being processed on board the MyRio and are using a lot of the capability on board. But what I'm going to do is run through a video here because what we did is we developed this not in 5 minutes, like actually 2.5 minutes, which was extremely fast. Margaret did it a little bit earlier. It took about 5 days to implement the MyRio onto the cube, a complex mechatronic system. That's actually pretty fast. That's pretty impressive, I think, for our team to have done that. And within 5 days, we were doing this, and we had to prepare for NIDays last year. Well, let's have a look at how we
Quanser Capable Explorer powered by MyRio. Now, let me take you under the hood a little bit and show you a little bit of the code. So as you can see, there's a lot of usage of those express CIs that Margaret mentioned. For all of the critical sub-functions, those express CIs really accelerate the development process. And also, when you do need a little bit more power, for example, for advanced flight control, this actually has auto-type control right now. We were able to implement those advanced algorithms using MathScript. So we actually have MathScript code running in real time on the NIDays right now. So before we go, Jeff, cameraman, we should settle it down. That was great.
So there you go. So that was at NI Week last year, and clearly went very well. Got very well received. And this product actually is an extremely popular product now. What I'm going to show next and then there's a blank screen. The reason is, I'm going to explain. This is an application. A lot of this work was done for Defense Research and Development Canada, in which we developed a bunch of tools where we can have multiple vehicles collaborating together. So what I'm going to do is, next slide. So what we're going to be seeing here is a project that took a few years back that is now possible using the MyRio, and I'll just sort of have you look at this first and then I'll describe a little bit further.
So essentially this is a demonstration mission for like search and rescue or anything like that. The two planes are going to be flying search pattern over the field. The blue guy will be flying as the leader and the red is the follower. The red will be generating a flight path on the fly and communicating that to the follower. So they'll be flying in a rough formation. That's going to be a tight formation. It's going to be loose, back and forth. When the target comes out and then they see it, the blue guy will tell the coordinates to the follower. The leader is the only one who has the camera. The follower will then loiter around the target position. The leader will start flying back and forth this way to tell the helicopter where the target is. The helicopter will then go confirm the target, confirm the location of the target, and relay that information to the ground vehicle who will then drive to the target. Once that's all done, then all the vehicles will return and land. So that's the mission that we're going to be flying. We execute it to make the effective and make everything work possible to use. Yeah, so actually models on the vehicle.
So what we have here, just to summarize quickly, if you didn't understand because maybe it's a bit noisy, we have a blue fixed-wing aircraft, a red fixed-wing aircraft, a quad-rotor, and an ATV, all-terrain vehicle, basically working together intelligently as a team in an autonomous way, identifying where a tarp is out there, sharing sensor information between each other, relaying information, until finally we have this ATV here autonomously driving over to the target. So we're talking about advanced systems, and this is all possible using platforms like the MyRio now. So really, what the message is here is that the capability is in your hands, the support is there, the organizations are there to support you, and we, by the way, that was a landing, it wasn't a crash. And really, the innovation at this point is really up to you. Thank you very much.
Thank you, Keith. So we have heard and seen a lot of applications in the control systems, but I know a lot of you here are in the communication field. One of the most interesting topics these days is software-defined radio. Usually, software-defined radio is designed in a way so that the algorithm designer would focus more on the algorithm rather than the RF side. And usually, the most challenging part in software-defined radio is the software, because you have to design the software in a way to fit the software-defined radio challenges and limited resources. And usually, you have to learn a lot of software, because sometimes you have to simulate your system using M files. You would need to implement your code on FPGA, then you have to learn and implement the HDL code. You may also use C or C++ to do the processing and the host interface. In addition to that, sometimes you may even have to go down into assembly to design the driver so that you can interface with the hardware. What would that happen? That will make the learning curve really low. You will have limited resources and you will need specialists. And this will result in increased cost and increased time to result. And what you really want at the end of the day is you really want to test your algorithm and see it working over the air to see if it's really working or not. Well, we have talked about LabVIEW throughout the day. LabVIEW solves these challenges because it's one programming language that allows you to program multiple processors and FPGAs. And that's allow you to simulate, prototype, and design your algorithm really fast. We have seen through the slides of Shaker, he has talked about the USRPs. The USRPs are the software-defined radio hardware that you can use to implement these kind of applications. But the old USRPs did not allow you to go into the FPGA and program it. It came with predefined FPGA code. So I'm pleased now to announce the latest product of National Instruments, which is the new USRP Rio, that comes with an open FPGA that you can also program using LabVIEW. So this USRP Rio, because it has the open FPGA that you can go and value, it is the most suitable product for applications such as 5G wireless prototyping, high channel MIMO, and wideband with low latencies. It features 2 channels to receive and transmit, so it comes with built-in MIMO. And it can give you frequency from 50 megahertz up to 60 gigahertz. As we said, it comes with a customizable Kintex 7 FPGA, and it comes with GPS clock so that you can synchronize the multiple USRPs together. Well, you can also share the clock of multiple USRPs and the local oscillator that allow you to do massive MIMO systems. So to now really see the USRP in action, I'm inviting Munzer, our applications engineer, to have it up and running. So the USRP Rio is connected to his laptop through Mixi. So if you can just switch and let us see how it works.
Thank you, Nancy. Good morning. So what you are seeing here, this is a template project that you can start with to program the USRP. So as Nancy was saying, you have 2 parts of programming. So you can either deploy a software on the FPGA, which is for example this one, or you can build the code on the host. And you can build both codes and you can interact between these codes. So I'm going to show you a little bit about, for example, for the FPGA part, for the radio interface, for example. So here it gives you access to all the inputs for the USRP radio, so you can use these to acquire some RF signals, and then you can do whatever type of algorithm that you want to apply on these. And here, for example, these are the FIFOs that you can use to send the data from the FPGA to the host, or vice versa, without losing any data and at really high speed. So first I'm going to open the FPGA VI to show you how it is done and the architecture for it. So here you can see this node gives you access to the RX INQ. So you can acquire your RF signal after down conversion. And here in this part, this is all the correction and the estimation to give you the signal that you can ideally use. And here you can apply your custom and own algorithm for signal processing, like a FIR filter, for example. And eventually this part of the code will help you to send the data to the host using FIFO that I already showed you.
So Munzer, so this USRP really gives you access from the analog digital converter up to sending this data back to the processor, right?
Yes, correct. So basically the data comes in RF, and inside this one, it's a normal RF device. The down converter takes data to baseband, and then you have data here in baseband. So you have it here on the FPGA, and then you can do your own signal processing and send it to the host.
So usually at the end of the day, this code is going to run on the FPGA of the USRP video.
Yes, correct. Now let's switch to the other code, which is the code that's running on my computer, that's taking the data on the FPGA. And here also you can have any type of algorithm due to the power of value. So here, for example, you are seeing this is an example of ODM modulation, demodulation. So you can see here the blocks from our modulation toolkit that helps you directly convert this data to whatever type of modulation you want. These are all the things that are applied in order to have your OFDM data, and eventually data is being sent to FPGA for generation. So I'm going to run this example just to show you how it looks like. So here what they are doing in this example, they are sending these symbols, and each time they are changing the order of the gram. And actually this is the receive signal time domain, and here you can see the constellation plot changing whenever we change the type of modulation that we are using to send data.
Thank you, Munzer. So using one platform, which is Lavi Graphical System Design, we were able to implement software-defined radio and program the FPGA and the host in one environment. So National Instruments provide a lot of platform for software-defined radio that goes up to good, better, best approach, or programmable with a common graphical system design approach. So with LabVIEW, you can implement your code on your SRPs, then later on, if you want to go more advanced into the research, the same code can be taken and implemented into more advanced hardware, such as the BST. So some of you may have already heard about the vector signal transceiver. When we have released the vector signal transceiver around 2 years ago, we really were kept to our mission that when we say we come up with innovative product, because the vector signal transceiver was the world's first combined vector signal analyzer and vector signal generator and FPGA in one device. And we keep on enhancing our product. So we thought about applications such as advanced LTE and 802.11ac that requires frequency ranges that go up to 160 megahertz. So with the release of the new vector signal transceiver, with the bandwidth that go up to 200 megahertz, you will be able to implement such kind of applications. Well, all our product relies on the latest technology, like the Kintex 7 FPGAs that we were talking about throughout the day, now is available for the FlexRio PXI modules. So if you want to implement your DSPs on PXI using the FlexRio, you will be able to implement it now with the Kintex 7 FPGAs. We have talked throughout the day about the MyRio, and Shaker and Margaret have said that the MyRio used the same system on chip as the industrial product. So the industrial product that was released based on the Zinc system on chip is the Compact Trio 9068. So this Compact Trio is using usually the latest technology in the field. So it has Kintex 7 FPGA in the chassis. It uses the dual-core Cortex-A9 processor for ARM, all programmable using LabVIEW. Also, in addition to that, we have seen and heard a lot of you that really like Linux. Linux is an open platform, free operating system that you can use, but it does not give you deterministic application that you need. You cannot really have deterministic application running on Linux. So we thought, and we have used all our knowledge in developing real-time operating system, and we have came up with a new kernel for Linux, which is the NI real-time Linux operating system that is running on the MyRio and is running on the Compact Trio 9068. So you can now use Linux and program with C or in LabVIEW. So with all this, I would like to finish it with the same video where we have started, where we say LabVIEW all system go. So with the new LabVIEW 2013, you are able to target FPGAs, processors, Linux operating system, dashboards, Android, and iPad devices. And we have added a lot of enhancements through the LabVIEW 2013. So through this keynote, we have seen a lot of the releases and the new product we have seen. But at the end of the day, our success is your success.